Okay, good evening, everybody. Welcome to CSYS5040, Criticality in Dynamical Systems. So this semester, we are going to be covering a whole bunch of interesting work in nonlinear dynamics. Specifically, the more interesting thing, which is where nonlinear dynamics makes for abrupt changes in time series. So most of time series analysis deals with processes that are continuous, that if they are in physics, they are generally thought of as being in an equilibrium. It's also true of economics. But sometimes our systems aren't in equilibrium in any reasonable sense. So we want to be able to have some pieces of analysis that allows us to understand what happens when our time series breaks. And so that's what this semester is all about. And in particular, what measures we can take, how we might understand systems, what might be their causes, and how we can model it. So before we start, just a bit of housekeeping. We are now certainly in these units, I think in most units in computer science, we are now running them all in in-person mode. So we no longer have Zoom active for our weekly meetings. They will be recorded. This particular room doesn't have recording facilities available, so I'll be recording them directly to my laptop and uploading them to the website. Keep in mind that, of course, sometimes that just doesn't work, and for various technical reasons. So, for example, tonight it wasn't clear that it would how it was going to operate. So all of the slides and work material will be available on Canvas, which I'm sure you've seen, but can't guarantee the videos will necessarily go up if there's some error that's happened that night or whatever. Okay, a little bit of admin. Just like to acknowledge traditional owners of Australia and recognise their continuing connection to land, water, and culture. Currently on the land of the Gadigal Nation, and pay respects to their elders past, present, and emerging. We are still obviously in COVID high risk, certainly not the crisis that we've been in for the 2.5, 3 years previously, but we are certainly still concerned about the spread of illness. So stay at home if you're sick, wash your hands regularly, avoid physical greetings if you can, cough or sneeze, elbow tissues. Probably don't need to keep, some of these things aren't perhaps as critical as they once were, but I'm going to leave them up there just so that you're mindful of people's personal space and their concerns for their health. And if you can, please keep everyone other people healthy. We're also just in the middle of a flu season. So flu season is actually a bit nasty this year. So I've certainly had my vaccinations. Hopefully you can get your vaccinations as well. But if you do feel sick, even if it's not COVID, it's just flu, the flu season apparently is quite nasty this season. So it might be an idea to take care of yourself if you think you'll even just run down with flu. Noting the emergency exits, obviously the exits there's exits at each end of the corridor, and then there is, I'm not sure where the gather point is from here, but there will be, if we do need to exit the building, there will be wardens that will be able to tell you where to go. So just some general housekeeping there. This is how the semester is going to look. So we're going to start today. Today's going to be a very, very general overview. I'm going to talk about some particular code in Mathematica. Mathematica is going to be the coding language we're going to use for this semester. So we're going to talk about Traditional ways of looking at time series analysis, how we might deal with problems, and how the problems that we're confronted with in the 20th and 21st century gave rise to the methods that we're going to be talking about this semester. Then going to introduce you to fractals and chaos. Third lecture is going to be on financial markets. That same week, the article review is due on the 20th of August. It's worth 15%. I'll talk a little bit about that at the end of class today. Fourth week, decision theory using stochastic equations. Week 5, artificial intelligence. It turns out that despite what you might have heard, chaotic time series can be predicted. So I'm going to talk a little bit about how artificial intelligence is able to contribute to that. Week 6, I'm going to talk about what are called distortions and potential functions. This is one of the ways in which systems can break in a certain sense, and how that might actually look when you see it in a time series. Then we're going to talk about recurrence plots and stability theory. That is on week 7. Note that the computational report is worth 25%. That report is exclusively in Mathematica. So by the time you get to week 7, you have to have understood at least a functional knowledge of Mathematica. I've given you tons of resources on the website. There are built into Mathematica. There are also tons of resources. So launch yourself into that stuff. If you don't practice it in your spare time out of class, you're simply not going to be able to get it with sufficient facility to be able to answer the computational report. Okay, so you have to get involved in it. The article review is more about getting your head into the right headspace. It's about you reading and comprehending some of the ideas that are going to be involved in this semester. So I just want to sort of bring you into the right headspace to be able to start working on this stuff. Note that most of the assignments are about a month apart. So you've got about a month between each one, roughly speaking. Week 8, tipping points and bifurcations. I haven't actually got a guest lecturer lined up for that yet, but we'll see how that goes. So either it'll be a guest lecturer or I'll be presenting some work on that. Week 9, I'm going to be doing a work example with recurrence plot analyses. And week 10, we'll be doing a worked example using housing markets. Week 11 is a compulsory attendance week. You have to turn up in week 11 to give your talk to class. This is, of course, in person now in this unit. So we're going to be running those in person where you actually give the presentation in class. Okay. And during that, you'll be expected to ask and answer questions from the floor. Okay. So I'll be watching who's asking questions, and you will be graded on whether you ask questions or not, how good those questions are. Having done 50-10, you'll know how this works. It is someone giving a presentation, you get to ask them a question, they get to answer, and depending on the quality of that, you get a grade. Okay, so there is only 12 or 14 students in the class, so we'll be able to get through that in one night, but you have to be here. If you don't turn up, then it's not clear what your assessment will be. Okay, but it will be problematic, and you'll have a fairly sharp discount on your grade. Okay. Then week 12, bifurcations in what's called the social icing model. One of the most famous examples in complex systems theory for how we understand how bifurcations and tipping points work in social systems. And then summary and wrap up for the final report prep. That's in week 13, final report due for 40% in that week, 5th of November. Okay, there are no group assignments. All of your assignments are individual in this unit. So when you're choosing your, I guess I mean, it's not necessary, but when you're choosing your article to review in week 3, you can do whatever you like for the article. Of the options that I've given you, you can choose whichever ones you like. It's not terribly important. But what you can do is you can, if you want to, you can use that week to choose a topic that you might be interested in for your final report. Okay, so you might want to use that as a way of starting to get your thoughts and thoughts in a row for what you want to be able to do sort of long term as you go down to the computational report. Doesn't require anything to do with your specific topic, but your oral presentation and final report do. Okay, so it might just make your life a little bit easier if you think ahead of what you want to be able to do early on in the piece. You don't have to, but it might help. Okay, so let's think a little bit about time series analysis. Anyone got any thoughts about what they think we usually do when we're interested in time series analysis, just in general? Why are we interested in time series analysis? Any ideas? Evolution of something? Yep. What do you, why would we be interested in evolution of something? Any thoughts about more specifically about why we want to do time series? Yep, predicting stock prices. That's absolutely one thing that we can do with time series analysis. Any other thoughts? Do we always want to know exactly what's happening in a time series? We don't know precisely, numerically, what's going on in a time series. Why might we not want to have an exact understanding of what's happening? Why is it kind of interesting? Sorry. Pattern? Yeah, that's one thing. Yep. Yeah. Yep. Okay. So did you say noise? Yep. Yep. So noise is a really good indicator of what sort of things do you think noise is a good indicator of? Oh, yeah, that's a good point. Yeah, signal to noise ratio. So how much signal you're actually able to pluck out of a time series compared to how noisy the data is. Absolutely. Anything else that we might say about noise? Anyone ever done linear regression? Anyone know what linear regression is in stochastic systems? Residuals? Yep. So what are we interested with residuals? No, that's right. No, I'm not going to ask you. I'm not trying to embarrass anyone, but I want you to start thinking. I want you to be happy to talk. That's what I want you to do. I want you to be happy to offer up suggestions without feeling been criticized. So, what is a residual? Well, it's usually the bit that's left over after we do a linear regression or some other regression. So we do some regression on some data, and the residuals are just the things which are different from our model. Okay. So does anyone know what we want our residuals typically to look like, at least in statistical analysis, sort of traditional statistical analysis? Do you want to know what we'd like them to look like? It's a particular type of distribution we'd like it to look like. Any ideas? What's the most famous probability distribution you can think of? Normal? Absolutely. Yep. So what we'd like our residuals to look like is to be Gaussian distribution, normally distributed. The normal distribution has got a couple of really nice properties. Probably the most important is that it's symmetrical, which means that if we look at either side of the mean, it looks the same shape. Okay. That at least tells us that if we're wrong, then we're kind of equally wrong on either side, right? Okay. So it's symmetrical. It's also got a rather nice property that the tails are nice and they decrease quite rapidly compared to other distributions or some other distributions, which tells us that typically it means we can integrate it, which means that we can find the area under the curve without having to have these really big outliers that cause all sorts of problems. So it's also got an interesting applied interpretation. Does anyone know what the applied interpretation is for what the fluctuations are in our regression models? Does anyone know how we might interpret those fluctuations? So we've got something like what have we got? We've got something like a regression model. What does it look like? Let's just say we're doing some sort of linear regression. So our regression line is our regression line. And what we've got is a whole bunch of data sort of around it like this, right? Most of it should sort of sit near our regression line, and there shouldn't be very much of it very far away from there, but there'll be a little bit up there. So it looks kind of like. But clearly, our regression line doesn't capture everything, right? I mean, it can't. It's a stochastic process. It's a natural process. Natural processes are quite complicated. So what do you think we interpret those random variations as being? Any ideas? We're measuring a system. So let's think about something a bit practical. We are measuring, let's say we're measuring the population, the average population, well, we're measuring the population height as a function of age. Okay, so we've got height and time in years. Okay, so down here you've got like 0. I don't know how big are babies when they're born, like 0.1 meters or something like that. Anyway, something like 0.1 meters, right? All the way up to I don't know, 2.5 meters right here. Yeah, 2. So we've got some basketball players out there somewhere, right? Up to 2.5 meters. Not very many people there. 2.5 meters, right? Generally speaking, of course, it's going to be probably not actually quite that linear. Like we grow in spurts, right? So we don't always grow linearly. But let's imagine that we do grow kind of linearly over time as we get older. So now, what do the differences? So our residuals are actually the gaps between our data points and the actual regression line, right? Okay, but what do you think they actually represent? What do what do these fluctuations, random fluctuations around the mean, around our regression actually mean? Like just a practical thought experiment. Sorry? Some range, absolutely. So when we think of range, so we pick a time, let's say, we pick a time, and what we have at that point in time is a bit of variability, right? So it's unlikely that if you're 3 years old, that you're going to be 2.5 meters tall, right? That's a tall child, I think, by any standards. And if you're 0.1 meters tall, that's a very short 1-year-old. So what we've got is a range, right? But what does that range mean? Like, obviously not. If we had 1 million 3-year-olds, we would have some variation. What does that variation actually? What does that actually measure? What's actually going on in the measuring process that's going on there? That's an interesting point. Is the height at some point in time stable? It should be stable. Yeah, it's not actually how I would have thought about it, but yeah, technically it would be stable. Yes, that's an interpretation. Any other thoughts? What influences how fast we grow? Why aren't we all the same height at the same age? Genes, absolutely. Anything else? Sorry? Nutrition, absolutely. Environmental factors, right? All sorts of things. So what's actually going on here is there's a contribution from genetics and a contribution from our environmental factors, right? So there's at least, well, those are actually the only two things which can influence any biological system. So we know that we could at least in principle break it up into two parts, right? If we wanted to, like this noise could actually be contributed to by two parts. And in fact, you could potentially say, well, maybe this isn't how the population across the entire world works. Maybe the population across the world could be broken up into those portions of the world which are undernourished and those portions which have a great deal of nutrition. And we could ask ourselves, well, now we actually might have a bit more structure. And we might actually be able to separate out our linear regression into multiple regressions, depending on which part of the world you come from. And that would then tell us something more fine detailed about what's going on in the system. And it would probably reduce the noise, right? It would probably reduce the noise in the system. So these fluctuations will get smaller because we've taken away some of the uncertainty. So other examples of where there are fluctuations. What about fluctuations in weather? So on a day-to-day basis, so rather than having a whole bunch of data points that are given at a given time, with weather, it actually is slightly different. So with weather, what we've actually got is something which is absolutely known at a given point on the face of the earth. What we actually have is a known temperature, and again we've got time, but let's say this is just 0 days out to, let's say, 365 days at a given year. And every day is a well-defined point, right? So there's no uncertainty in the day, but the next day it'll be slightly different from the day before, or it might actually be the same, of course. But we'll see a trend as I try and get the sort of thing we might get in a linear regression. And so the actual days look like this. And there's zero uncertainty in the temperature at a given location. but we could put a smooth line through it. And the uncertainty and now what we've got are changes over time, which are different from that regression that we've got in the temperature, right? So now what's our uncertainty? What do you think that the fluctuations in this might actually now represent? The statistical fluctuations in this might actually represent? What influences weather of temperature from one day to the next? Pressure, yep. Solar flares. Humidity, yep. Seawater temperature. Also, if we are looking at a physical spatial point in time, right? Oh, sorry, point in place, it's surrounded by other points in space, right? So it's also influenced by what? Its nearest spatial points, right? So it's not just influenced by this point here is going to have a temperature which is going to be slightly different but similar to the point here. It's going to be similar to but slightly different from the point here and the point here. And the further away we get, the less correlated this becomes with all the subsequent points, right? So now we can think of a whole bunch of factors which are influencing the daily temperature changes. And the daily temperature changes are changes in atmospheric conditions, solar conditions, a whole bunch of things that we contribute to, such as pollution and smog in the air, fire will influence temperature. Cloud cover, of course, will influence temperature. But of course, nearby temperatures will influence temperature as well. So now we've got a completely different interpretation of what we mean by the fluctuations that we're looking at. Like there's literally no uncertainty in the measurement that we've taken on a day-to-day basis, but we still actually get some variation. Okay, and so in some technical sense, there is zero uncertainty in the drivers of temperature, but there is uncertainty as to what it will be the next day. Okay, now famously, that's where we first got chaos from. It was a weather prediction model, and that weather prediction model turned out to have these really strange patterns to it. Okay, so first of all, we're going to talk a little bit about not so much stochastic things like this with statistical variation in them. We're going to talk about the deterministic versions of change. Okay, and then we're going to use that or its problems to motivate why we're interested in statistical versions of that, and then ultimately end up to where we were about somewhere around about 20 years ago, let's say, something in that order, in terms of how we understand large-scale movements of some practical systems and why it's non-linear. And then the rest of the unit will be about using modern techniques to try and measure and understand these sorts of fluctuations. Okay. Okay. So, time series analysis, truly vast field of study. Many different subfields: econometrics, psychology, behavioral sciences, physics. Often very technical and needs a lot of experience in a particular field to be applied to. So this motivates why we use Mathematica in this particular unit. Mathematica does have a little bit of a steep learning curve to get used to the coding environment. It's not terribly steep, but it's one you have to get over in order to use the tool. The reason why we use this tool is because it is probably the only, or certainly the most user-friendly tool for doing very complex mathematical problems in a very straightforward way. Okay, so that's the reason why we use it. the goal for your understanding of the code isn't actually terribly high. What you need to be able to do is use the code well enough to be able to implement the code books that I'm going to give you. If you've ever used Python, it's like a Python notebook. You can simply execute lines of code and adjust those lines of code to the task that you have at hand. Okay. Now, that comes in a multiple sort of set of varieties. You can use it in a very vanilla way where all you're doing is changing the constants to see how the constants change the way the system moves over time. Or you can build on what's in there to actually apply it to then different systems with different dynamics, with different interpretations. There is no reason why you shouldn't be able to achieve an HD in this class by simply coming up with clever ideas to change the code that I'm going to provide you in a way that allows you to tell me that you understand something good. Okay, you get HDs for being clever, not for writing massive amounts of code. Okay, so that's what I want to impress upon you. You don't need to know Mathematica very well, but you do need to be thinking. I want to see you guys think. Okay, that's the important thing for me. So, time series in complex systems builds on this background of things like chaos, fractals, what are called heterogeneous particles or agents, and emergent properties and mid-level interactions between agents or elements in the system. So essentially, a lot of the things that we covered in 5010, but you don't need 5010 to understand what we're going to be doing in this semester. You can do it all directly from the notes that we're going to be working from. And we want to narrow down on the task that complex systems is useful for and focus on tools and concepts rather than technical foundations. We're still going to need some maths, but it's not going to be terribly much. And we can understand the maths through applications quite readily. And so thinking of time series in a different way to the usual approaches that would be necessary in order to get to, let's say, a third or a fourth year undergraduate maths degree, which is usually where we'd start doing some of the nonlinear stuff. We want to be able to do that in a semester, leveraging off modern computational tools and some really interesting applications to start playing around with these ideas. Okay. So thinking about the two elements of this. So dynamical systems theory is one element of this course, and the second is statistical time series analysis. So those are the two components of the system. And in fact, the equations that we're going to be playing with, I'm going to describe to you today, one part of it is the dynamics part of it, and the other part of it is the statistical part of it. I'm going to break those up into two particular pieces of mathematical ideas. And then I'm going to show you how you actually implement directly in a piece of Mathematica code in a way that allows you to see where the dynamical part exists and where the fluctuations part exists in the code. So in the dynamical part of it, we have mathematics of paths on surfaces. So if you look at that graph on the side, you'll see there's a red curve and a blue curve. Those are the paths over a surface. That's a dynamical system. Each path is a single time series. We were also going to talk about bifurcations, chaos and fractals, and smooth dynamics based on an underlying theory. So dynamical systems is the smooth part of the theory. On the statistical side, we've got mathematics and a bit of data. Again, bifurcations and fractals based on dynamical systems theory, but focusing on the statistical dynamics that come from data time series analysis rather than sort of the more typical deterministic systems. And so the thing that I want to sort of try and bring home to you as clearly as I can is that a lot of the things that have spatial properties. So for example, if you look at a tree, clearly it's a system that has some interesting spatial properties, right? So trees were one of the first examples that people looked at to try and understand the way in which fractals might work, branching systems might work. The same thing is also true for the lungs and our blood vessel systems, our brain, those sorts of things, they all have these quite nice sort of spatial, fractal, nonlinear structures to them. But of course, these structures emerged over time. So whenever we see these structures in space, they are a consequence of some process which has occurred over time. And so what we are interested in is understanding the relationship between the spatial structures or some other structure of the system as it unfolds through time. Okay, and those two things are very tightly coupled to each other. Okay, and in fact, our whatever our variable of interest is, it's either a spatial variable or it's a temperature variable, or it's going to be a financial variable. These are going to be a function of time. So literally, it's going to look something like x of t, it's going to look like y of t, which just says that we've got something here, x or y, on that axis, and we've got time on this axis. Okay, that's going to be the most typical way we have it, with one axis being time, another one being some other dimension. But we can also have a system in which we might have, in fact, two variables of interest or more, so that we actually have is x of t on the x-axis, y of t on the y-axis, and we have a relationship between x and y, but that relationship between x and y is changing over time. Okay, so from one time step, it has this value. At some other time step, it has this value. And the third time step, it has this value. And so the system actually looks like that. Okay, so this is a point here, x of t, y of t. It's called an implicit equation because it implicitly relies on the fact that time is built into x and y. Okay, and so it tells us we can actually now draw an arrow. And that arrow is the direction of time. Noting though that what we've plotted here is not a plot of time, it's a plot of x and y. Okay, is that fairly clear with everyone? Okay, so this is the sort of thing that we're interested in, and typically what we're actually going to have, we're going to call this something like f of x, y, t. It's usually the sort of thing that we're going to be playing. Okay, sometimes the t is implicit in the x and y, sometimes it might be explicit, and we're actually be able to talk about it independently of x and y. Okay. Okay. One of the other rather interesting questions is this qualitative or is it quantitative work? It's a bit of both. It's a bit of both. We have been interested for a very long time in not just how the precise numerical values of a system evolve, but what the qualitative features are about a system which communicate to us something really important about the system. Okay, and what do I mean by that? Okay, time series prediction of weather has gotten much better over the last 30 or 40 years. So we've gone from being sort of to predict about 4 days into the future about 30 years ago. We can now predict fairly reliably about 7 days into the future. Okay, fairly reliable. But what we have gotten exceptionally good at is not, in fact, being able to do something which looks like let's say we're looking at temperature from today to 7 days time. Okay, and so we'd expect that, given that we're in a particular season of the year, we'd expect the temperature to be relatively constant, but to be kind of fluctuating, and it might go down a little bit as a cold weather system comes in, and so we've got a sort of general trend down like that, right? So that would be like a 7-day prediction with a little bit with a nonlinear regression going through it. Okay, but what's actually going on here is a little bit more interesting. Let's say this is at this is in the Sydney Basin, right? And so this is the Sydney Basin here as a spatial position. Okay, and let's see if I can do a horrible map of Australia. It's going to look like something like this. How does Australia look? Something like this, right? It's got a. It's actually not bad. Well, it's horrible, but it's better than I thought it would be. But what's going on here is, of course, what we've got are a whole bunch of competing sort of weather systems, right? No doubt you've seen the maps and what have you. The uncertainty that we have now is much less to do with simply not knowing what's going on, but not knowing precisely how these large structures start interfering with each other. What we actually know is quite a lot about the broad features of these weather systems, but we don't quite know precisely what the timing is with which they're going to move relative to each other, and what precisely the impact is going to be on the temperature in the Sydney Basin. Okay, what we understand really quite well now, particularly through a lot of our radar imaging and the explosion of high throughput data analysis, we have a really clear understanding of how these systems actually look on a given day, and how accurately we can predict them into the future is based on the fact that these actually do have some long-term patterns which are better understood, but it's the way in which the patterns that we know exist sort of interact with each other which is causing the problems. Okay. In the past, what it's been is we didn't even know necessarily that these structures existed, and that produced a huge amount of uncertainty because we simply didn't have the data. So if you go back 50, 60, 70 years, we simply didn't have satellite telemetry from which we could do the analysis, or the supercomputers to do the predictions and various other things. So those are the sorts of things that we're continuing with these days. It's much less to do with the predictability of weather as a whole, more to do with the lack of predictability with the way in which known weather systems collide with each other and what that impact is. Okay. Avind Earl is a very famous artist. He's responsible for probably some of the greatest backdrops in the Disney films during Disney's golden era of the 1950s, 1960s. And he used very specific fractal structures to give a sense of life to the backgrounds that he painted for Disney. And so if we want to think about how systems look naturally, we tend to think in terms of fractals. So again, spatial structures that are evolving over time give rise to some of these patterns of complexity. If you are interested in real-time dynamic generation of models, for example, in a lot of world building generative gameplay, what we're usually, not all the time, but in a lot of those games, what we're using is fractals to generate imagery in real time to make them actually look realistic without having to pre-develop them before, for example, a character turns up on a scene. So here we see qualitative features coming through in a different way. One is to produce, in this case, it's to produce natural-like scenery or natural-like proportions that allow us to find the environments more either aesthetically pleasing or more realistic. And those are qualitative features rather than quantitative features. So this is the sense in which it might not be quantitative in the sense that you mean with tradition. But I also want to emphasize that when we look at these things, there is always some process going on underneath that we are challenged by. So here, I think that top line graph is something like temperature across the Amazonian rainforest. But in order to understand the temperature in the forest, it is generated by CO2 coming into the forest being processed by the plants there, as well as the river systems and the alpine systems, and all the biodiversity within that system to be able to generate a single line, right? So I want you to imagine just how complex those sequences of processes are that give rise to the dynamics that we observe. So one way in which we can interpret fluctuations is all of those things that we can't explain easily through our representation of the microprocesses. Okay, so how many microprocesses are going on inside the Amazonian rainforest? Trillions upon trillions upon trillions. What processes can we take account of? Things like existing weather patterns, things like where particular river systems are now they're interacting with the ground, and of course pollution from nearby cities, all sorts of things. So all of those things influence it, and we may only be able to capture some of the drivers of the dynamics, and everything else essentially becomes noise. Okay, but that noise doesn't necessarily mean it's impossible to describe. It just means it's all the data that we can't easily describe. Okay, so let me see. Okay, so why criticality? What did we have before criticality? Where does criticality come from? What types of criticality we'll look at in this course? And in particular, one of the most important things we're going to be interested in this course is the relationship between surfaces and motions on surfaces. Okay, the reason why that's important is because our surfaces change over time, or we're going to use surfaces that might change over time. So I want to talk a little bit about how all of this becomes important. I want you to consider this nice mathematically shaped bowl. And this bowl has a force of gravity coming down from the top. And what we can do is we can just put a ball somewhere on the surface of our bowl, and we can ask, given the way gravity acts on the ball and where the ball starts from, what's the ball going to behave like? And of course here, the ball is going to naturally drop down towards the middle. So if we were to trace the ball as a function of time and its distance from the center, what do you think it would look like? So in this case, what we would have on this axis, so let's say we would have height on this axis, and we would have radial distance from the center. We'll put 0 there. Okay. What do you think this is going to look like? In fact, we'll do this in 2 different ways. We'll do it like that. We'll also do it as a function of time. And we'll do it as radial distance as a function of time as well. Well, let's just look at the first one. So now we're looking at radius and height. What's that going to look like as a dynamical system? What's our ball going to do? So we're going to start at radius somewhere here, and it's going to have a height there, right? So that's where the ball is now. So what's our dynamical system going to look like? If we start looking at the relationship between height and radius, what's this going to look like? What's it going to look? So how should I draw it? So it'll come down, it'll get to 0. Yep.
Wait, oh, that's
yeah, so 0 radius, right?
oh, so that's negative.
Yeah. And then it's going to come back up, yeah?
Yeah.
Yep, absolutely, right. And then all it's going to do is it's going to rock backwards and forwards, right? Because we're just going to assume there's no friction at the moment. So it's going to rock backwards and forwards. Over time, what's it going to look like though? So let me actually extend this a little bit. So this is our time axis, and this is our radius. And our radius, and now 0 is going to be there, right? We're going to start with 0 there. But of course, we're so, oh, actually, I started with negative, so let's start with negative again. So start from some negative value. What's going to happen now? And look at that, yeah. Right. So you can see that if we compare, or I should have kept the other plot, the other plot looks like this. We can see that this is a function of height and radius, where height is a function of t and radius is a function of t over time. So we've got height and radius as a function of t. But now we can also pluck out radius by itself, and we can start plotting the radius over time. Okay, so we've taken an implicit time variable and we've made it explicit by making an axis for it. Okay. Is that cool? All right. So, what if we change the shape of the surface? The implicit graph will shape. Yes, exactly. Yep. Depends on whether it gets over the hump in the middle. So it'll either go up and down inside the hump, or it might go over the hump, over the other side, and back again, right? It'll either trace one half or both of the humps. Yeah. Is everyone okay with that? Yep. Okay. What happens to the, so we know what happens to the ball that's on the edge. What happens to the ball in the middle? Nothing. Nothing. What if we give it a very small tap? So it will immediately travel from where it is, and then it'll eventually come back almost where, well, if you come back to where it's, yeah, depends on how much force we give it, right? If we give it an infinitesimally small force, it should come back and rest almost precisely from where it started from. Maybe, depending on how small or large that force is, it'll either tip over to the other side and trace out a W, or it might, if we get it exactly right, rest to where it started from, if our force is truly infinitesimal. What if it looks like, what if it looks like this? And again, we put it on the edge. What happens to the ball on the edge? Nothing. Now it depends quite a lot, though, on whether we nudge it to the left or to the right. Yeah. So it'll either run off to infinity, or it goes to the middle point. Okay. Okay. So if we have a look at what we've got here, what we've now got are two balls which are at the same spatial location. They're at the same spatial location for 6 different plots of what's actually the same structure of equation, but all I've done is I've changed one of the parameters. And I've changed that parameter slowly from left to right, and then the top, and then left to right from the bottom. Same structure of the equation, but it's got a single parameter that I've allowed to vary. And what, of course, I would like you to notice is that if we start with the top left, the ball on the left-hand side is in a nice stable position. If we nudge it, it essentially just stays roughly where it started from, right? But the ball in the middle, if we nudge that, it's going to move quite dramatically to somewhere else. As we've changed whatever this parameter is that I've allowed to change in the background, we see that dynamics actually become a little bit more interesting over time. At some point, this actually turns into a flat plane. Okay. And then if we nudged either of the two balls, they'll just slowly move off into the distance. Okay. Until we get all the way down to the bottom right, where if we nudge the left-hand ball, it either goes to the middle or goes off to infinity. If we nudge the middle ball, it largely stays just where it was. Okay. The point I'm trying to emphasize here is that it's the same equation with just a slightly different parameterization. okay? And almost all of regression that we ever do is about trying to find those parameters, okay? Now, if the system that we're interested in has one of those parameters which is not fixed in time, okay? And this is one of the biggest assumptions in most of what happens in statistical analysis. It presumes that the parameters describing the system remain constant. If instead we allow one of those parameters to change over time, we can end up with nonlinear dynamics which change the stability of our system. For the same spatial location, we can get multiple different types of stability. And it's those stabilities, switching stabilities in particular, that we're interested in a lot of the dynamical systems theory that we're interested in. Criticality in dynamical systems that we're interested in. Does all that make sense? Anyone got any questions about all of that? Okay. Okay, so here's some of the things that we want to talk about. First of all, I want to talk about geometry and calculus, the old school stuff, analytical geometry and calculus. Then we're going to move on to stochastic time series, which is the newer of the old school, where things aren't smooth, fractals emerge, and there's more than one way to skin a cat. So how old is old school? 1637. So we're going back a little over 400 years. Descartes asked, where did I leave my keys? Okay. Up until Descartes asked that question, we couldn't say where our keys were because we didn't have a bloody coordinate system. Okay. So what we wanted was a way in which we could relatively locate things in space, and ultimately it would turn out to be in time as well. Okay. What we actually had was a really sophisticated idea of geometry. Okay. But note that all of Euclid's geometry and what happened afterwards are all relative structures. Okay, so when we talk about 90 degrees or parallel lines, intersections, concurrent curve, all those sorts of things, those are all relative statements about positions in space. There's no absolute reference frame. Okay, so when we started to understand shape, our shapes were independent of where they sat in the world, so to speak. And in fact, the reason why we believed that turned out to be a really important concept in mid-20th century physics. The reason why that is because physics works because of what are called invariant properties in physics. Okay, so in particular, what are called invariants. And so a thing is an invariant if it is a thing that if you change it, it stays the same. Okay, if you change a property of it, it actually remains same between them. Okay, so what is something which is invariant? Well, our laws of physics, our Newtonian laws of physics, are all spatially invariant. They are true, we believe, essentially anywhere in space, excluding, let's say, quantum mechanics and black holes. Okay, broadly speaking, Newtonian mechanics works anywhere in the universe, or at least is a good approximation, almost anywhere in the universe. That's really important. If that didn't hold, then we couldn't say things like an apple falling from the tree or moons going around planets. We couldn't say that those could work generally anywhere that we were looking at them. Okay, and that was absolutely critical. They actually come from a series of conservation laws that were discovered, first described by Emma Noether, and she was one of the greatest early theoretical physicists who dealt with this. So usually we think about things in terms of conservation of energy. That's probably the most important one we think about. But it turns out that almost all of the laws of physics are based on some conservation property. And those conservation properties are directly related to invariant properties of systems. Okay, so shape is a spatial invariance, okay, at least in Euclidean space, in sort of X, Y, and Z space that Euclid came up with and Descartes dealt with. So if we move our parallelogram to some other point in space, it's the same parallelogram. We don't need to know where it actually is. And that's okay, but it turns out that if we want to do anything to do with calculus, we actually need to know where things are, right? So when we talk about rates of change, which is what calculus is all about, we need to know where things started from and where they ended up. And if we know that, then we're going to need to locate them somewhere relative to each other in some invariant metric space. So that's why Descartes came up with Cartesian coordinates. Cartesian coordinates are named after Descartes. So we moved from objects to locations. And in fact, what we have on the left-hand side are specific objects. They are considered to be solids of some sort. On the right-hand side, that's now been abstracted away. What we've typically got are locations. At those locations, we have an object most of the time, not always, but we have an object. But we've sort of abstracted away the shape now. Okay? Now all we're talking about are positions and changes in position. So we've now moved from the aspect of structure that are invariant with space to non-structural things, far more conceptual ideas that are now sensitive to their location. Now, as it turns out, most of what we talk about in modern complex systems theory is actually Descartes recut. Okay, so in modern mathematical objects, we often don't actually deal with coordinate systems. So social networks don't have an absolute reference frame. They don't have an XY position. They're simply some abstract nodes in a space that are linked to one another. Okay. Sometimes we give the distance between those nodes an interpretation. But most of the time, most of the times they don't have an interpretation. And there's simply these abstract algebraic structures, mathematical structures, which do not sit within a spatial ambient space. Some fractals are not structural in the sense of having Cartesian coordinates. Some, not all, but some. And there are some interesting special examples where they do have a certain type of spatial structure, but what we're actually interested in is not their absolute position, but we're interested in their change in position. So this is what we talk about when we talk about the percentage change in prices. That's what we are most often interested in when it comes to financial markets. We don't, generally speaking, really care very much about the actual price of something. What we're interested in is change of price. Okay. The interesting thing about these is that they do not have properties that Newtonian analysis allows us to study them with. Okay, so we need to come up with new tools. But let's see what Newton actually says about these relative positions. So Newton's first really significant insight was that any arbitrary function that we could possibly want to write down, no matter how complex it is, almost how complex it is, we could write it as a sequence of functions, of simpler functions. Okay? So f of x up here could be something incredibly complicated. Or we can break it up into a set of smaller polynomials, okay, simpler polynomials. And so what does that look like? What does that look like? Well, does anyone know what the simplest possible polynomial is? Yep, thank you very much. Equals some constant. Let's say c equals 1. Okay, so f of x equals 1. Oh, simplest possible polynomial. Okay, that says that f of x is just some value constant over time, nothing terribly exciting. Second most complex one has, in fact, it won't have something on the front. The next most simple one will just be, let's call it c1 times x. Okay, so what we have here is some constant. The b is not anything we need to worry about too much, but raise to the power of n. Okay, n is the power of our polynomial. So here it's going to be 1. When we had this is 1 times x to the 0, of course. That's the 0th polynomial. Okay, and now we can do for arbitrary f of x, we can actually just expand it outwards. And of course, this is really obvious for something like f of x equals 2 plus x squared plus 23x cubed minus 0.5x5. So that's clearly a polynomial, right? And if this is the whole polynomial, then we could obviously find all the terms that are interesting in here. We only need n to go from 0 up to 5. So instead of infinity, we can just have 5. Okay? But nothing terribly exciting. It's less obvious that it's also true for something like this. It's not necessarily obvious that a cosine can be represented as an arbitrary sum of these polynomials. Okay? So, if we want to start thinking about that, what we can do is we can try and find a of an. Okay? This is the thing that we often can't find, right? Or we need to think about a bit more carefully about how to find it. But if we wanted to find it, one way to do it is that, let's say we assumed for the moment, that we are looking at a0 plus a1 x plus a2 x squared. Okay, this is our f of x. Okay, and we don't. So this is what we want to find our f of x up to some second order. That's how we describe it. This is f of x to some second order. But maybe our f of x, we don't know what it is. It might be that cosine we were looking at before, and want to convince ourselves that the cosine actually looks like this to some extent. Okay. How would we find what a 0 is? Actually, I do need to cheat at this point. How do I want to? I do need to add the d back. How do we find out what a 0 is? Well, we set f of x to equal b, and we end up with a0. Okay, and our a0 term just pops out immediately by putting that into our equation. Next, before we do that, we can actually differentiate. We can take df of x with respect to x, and we end up with a0 goes to 0. Now we end up with a1 plus a2 x minus b squared times 2. Okay, no problems. And now we do df of x equals b dx. This equals 0 plus a1. Okay. So what we need to do is we need to take our function, and maybe our function is that cosine, and we can build up an arbitrary number of these, and the more and more terms we add, the closer it gets to being accurate. Okay. And so, in fact, for the cosine, we need to keep an infinite number of these terms, because in fact, n now needs to go to infinity for this to be accurate, or as accurate as it theoretically needs to be to describe the whole function. But in fact, the cosine function can be completely described by a polynomial like this. So it's not just that we can describe conventional polynomials, but arbitrary functions that we would usually be playing around with. Okay. And so if we were to write this out, this is how it would look. If we were to write it out, we can now say that in fact our a terms are actually f differentiated n times with x set to b by some n factorial that actually just pops out my differential terms, which equal. And we actually have our complete expansion that we need. Okay. So what this says is that any function is a linear combination of these higher order polynomials. And I say linear because it's literally summing up these higher order polynomials. Okay. So the polynomials themselves, x2, x3, x4, those themselves aren't actually linear, but we've got a linear combination of those non-linear terms. Okay. So just as an example, we can do this with e to the x, and we get the well-known equation. Now e to the x expands outwards to infinity as a polynomial approximation. And if we plug that into any plotting calculator, we see that the red curve, which is our approximation to the blue curve, our red curve goes to be very bad, goes to a linear approximation, goes to a order 2 approximation, or 3 approximation, or 4 approximation, each time looking closer and closer to the exponential function. Okay. So now Newton's second big insight. So not only was Newton interested in how we expand equations like that, but he was also interested in, of course, physics, what he's most famous for. And he was interested in a system's rate of change. And if we could describe a system's rate of change, we can actually say a huge amount about that system. Okay? So what he said was that if we can look at a system and we can look at how a single property changes over time and mathematically describe that rate of change over time, which is the thing that we can measure, then we can take that rate of change and we can find out what the original structure of the equation was given that rate of change. Okay. Of course, this is going to turn out to be nothing more than integration, but this is how he started to think about how we actually go about finding out how integration really works. So we've got a rate of change of something over time. Okay, so this is just our rate of change. We're going to measure that numerically by doing some experiments, and then we're going to turn that into a function. Okay, we're going to estimate rates of change as a function. Once we've got that function, we can start to approximate f of t, which is this is the thing we actually want to be able to find. We can estimate f of t at one time step into the future by looking at the previous time step, going forward some distance h, and looking at the rate of change. Any idea what that might look like if we were to try and plot that? It's a triangle. It's the hypotenuse is this function. Yes. So what does that look like? What we've got is our f of t. This is where we started from, which is our f at t0. This is our starting point. And now we're going to move forward one step h. And we're going to take the gradient. That's all that second term is. So in fact, it goes up like this. So this bit here is exactly what we've got there. Okay. And these are the other two sides of our triangle. Okay. So what he's saying is that what we have is, however complicated the original f of t is, we can approximate it by saying it's just some linear equivalent of our system. That's not great. It's good. It's a massive step ahead, but it's not everything that we needed. What he then said was that we could start from here and we could do the same thing all over again. And we could compute it again and again and again. And what we get is a curve. Okay. So we've gone from a gradient to a curve, which is exactly what we want. Okay. It's not a perfect curve. It's like a linear approximation. Every h distance into the future, we get an approximation. But this is what it looks like. So our change in ft, delta ft, f at t1 minus f at t0, that's this gap here. And then our delta t is t1 minus t0, this is our time step. And so delta ft divided by dt, delta ft, delta t, equals f of t minus 1, f of t0, t1 minus t0, and that is our approximation to our gradient. Okay, so what we're doing here is we are building our gradient, our linearized gradient approximation to what's actually going on in the system. It's not going to be perfect. This is the true, starting from this position, this is the true curve. What happens though as h goes to 0? So as this term here, notice t1 minus t0 h. So this term here goes to 0. What happens to this structure here? It goes to the blue. Exactly right. Exactly right. So that's how Newton started thinking about the way in which we can pull these functions apart. Okay. And so once we've got f at t0, h step into the future, h step into the future, h step into the future, evaluated at t0, t1, t2, we've simply got a linear combination now of gradients as our approximation. Given that we only ever knew the gradients of the system, we can now get the actual dynamics of the system out. Okay. Okay. So we now have two ways of thinking about this problem. We can now think about it in terms of the sum of a lot of linear approximations, or we can just keep higher order terms and we will get better and better approximations to a polynomial that gets closer and closer to the actual thing that we're. So these are the foundations of almost all modern science since the 17th century. They are linear, they are continuous, they are linear in the sense that they can be decomposed into a linear combination of other terms. Okay? They are continuous, which means we can differentiate them. And we can make quite reliable predictions for apples, artillery, the solar system, moon orbits, and in fact, a lot of the work up until somewhere in the order of at least 1900, there or thereabouts. 1900 is where things start getting a bit complicated. So the key point here is that calculus is the breaking up of a complex nonlinear problem into an infinite number of linear pieces that are smoothly connected to each other. Okay. And then adding the linear pieces back together to get the solution, or at least a good approximation to the solution. So Newton and Leibniz and all of those characters around that time, this is essentially what they were doing. They were finding ways to break up a problem into linear components, adding them back together, and coming up with some interesting solutions. So what are we missing though? Newtonian laws are perfectly smooth, which means they are differentiable. We simply don't rely on that anymore. Okay. We don't rely on it for things like evolutionary processes. While we like to think, or we had originally thought of them as being deterministic processes, we now model them as stochastic processes. Financial markets are stochastic processes, or in fact, if we look at, that's not that one I'm looking for. That's not that one. It's this one. If we look at a single pollen suspended in a whole sea of pollen, just by observing the one piece of one pollen particle as it evolves over time, it traces out a stochastic path And it traces out a stochastic path because of, depending on what you're trying to model, it's either being perturbed by other particles of pollen, or in this particular case, what's being disturbed by are gas molecules. Okay, so you've got a little bit of pollen suspended in water or in the air, and either the water particles or the air particles are constantly bombarding it. And those constant bombarding, we don't see the actual individual particles hitting it at all, of course. We can observe the pollen because it's large, but the gas particles, the water particles that are making it fluctuate all over the place, we can't observe those. And because we can't observe them, because there's billions upon trillions of them, we can't even in any sensible way hope that we would ever measure them. So we approximate them with a stochastic process. Okay. And so that's the next step in what Newton did. Sorry, not Newton, and what Einstein, well, it's not even going to be Einstein. It's going to be a guy called Bachelier. But before we get to that, we need to think a little bit differently about these equations that we had before. So before we had this rate of change of f over time, and so this is our rate of change function, our gradient function. And we want to rewrite this a little bit differently. If you're a mathematician, you kind of flinch when you read that because this is what physicists do. They simply say, it looks like a fraction, so I'm going to treat it like a fraction. But in fact, if d of f divided by dt is not a true fraction. It's a nice way of thinking about it if you're not being terribly precise. Mathematicians say it's a linear operator function. d dt operating on ft is a linearization function. So it's not quite what's going on. But what a physicist would say is that we'll treat it like a fraction. In fact, we can rewrite it this way. We can write d of ft, we're going to take the dt to the right-hand side, there, next to the ft. That's all we've done. So that's the nice practical way that physicists rewrote it. And if we can now take this and we can now integrate over d of ft. If we integrate d of ft, we get ft, left-hand side. On the right-hand side, we get the integral of ft dt, which is nothing more than conventional integration. So nothing terribly fancy there. But what's important, and so this is just a working example of doing exactly that. But what's important here, as far as we're concerned, is this structure here. D of ft equals f of t dt. We want to start thinking about this a little bit more carefully. Okay? That is this notation here. Okay? D of ft equals 1 plus t cubed plus 0.5 t7 dt. This says that an infinitesimal change in f of t, capital F of t, equals this complicated polynomial times some infinitesimal value of time. Okay, that's what's going on there, at least as the physicists would say. And we want to be able to look at that a little bit more carefully. Well, what we can now do is, rather than just say d of ft equals f of t dt, d of ft equals f of dt, we now want to add this term on the end here. Okay. This is the insight that comes from what Bachelier did, and then what Einstein did a couple of years later. That is, we take something which is classically deterministic. This thing here is completely smooth and deterministic. We're going to add on to it this thing here, which is going to turn out to be a noise term. Okay, it's going to add to our system some fluctuations. And so how do we think about those fluctuations? What do those actual fluctuations mean? Well, it's actually the rate of change of a Wiener process. Okay, so a Wiener process is a stochastic process that we can sample when we're looking at Brownian motion. And what do we mean by sample? Well, actually, it might even be on the next slide. So, yes, it's on the next slide. What it says is that we're gonna assume that the noise, that little bit we've added on the end, that noise is going to be Gaussian, normally distributed noise, okay? And what we're going to do is at every single infinitesimal time step, what we're going to do is we're going to sample that distribution. So what we're going to do is at time t0, we're going to randomly sample this distribution here. And so maybe we can get this value here. Let's say negative 1.4. Okay. And so that's got a probability associated, right? The interval has a probability associated with it. And so we sampled this distribution. It came back and it said that the value came back at 1.4. Then at T1, we're going to sample it all over again. Okay? And maybe this time it comes back as positive 0.1. Okay? Now we've got two random points. Okay? And that's going to be our WT1 minus WT0. What's happening there is we're randomly sampling this distribution at each time step. And what we're then going to do is we're going to take the difference between it. Okay? But now what we've got is a stochastically varying change over time. Okay? What is going to impact that most importantly? What do you think is going to impact this? We're going to assume it's Gaussian. So what are the things that are going to impact this thing here most important? Variance. Yes, exactly. Ultimately, we're going to assume, because this is what we do all the time, that we've essentially regularized so the mean is on 0. And it's just going to be the variance, which is going to be interesting to us. So in the same way as our time goes to dt, so a change in time step, or the delta in a time step goes to dt in some nice theoretical limit. The argument is that two samples of our distribution goes to this thing called dw. Okay, that's our Wiener process. Okay, and now if we integrate it, as we did before, what we end up with is an integral of the deterministic part plus an integral of the stochastic part. Okay, none of which ultimately needs to worry you, except that this sigma term here changes the strength of this thing here. And this is the variance. Okay, so it's the variance which changes how big this is. So we assume that it is a mean of 0 and a variance of 1, but now sigma actually spreads this upwards and downwards, actually changes the variance, changes the strength of our noise. If sigma is large, then we end up with wide variance. If sigma is narrow, we end up with very narrow variance. And so with small sigma, what that's going to tell us is we've got very little noise in the system. With large sigma, we have huge variances. So someone mentioned, I think it might have been you mentioned earlier in the lecture, a really important relationship. What is the most important relationship across this entire equation as far as trying to understand how much information we can extract from the system? Absolutely. The bigger the sigma is, that's not actually hugely important in and of itself. What's important about this is its relative size to this term here. Let's say if this term turns out to be, in its integral, a value of 1 billion, and this is 0.1 in its integral, then the 0.1 means nothing. But if this turns out to be 10 to the negative 10, and this is 0.1, then this is huge. Okay, it's the relative values between these things which makes all the difference in the world. Taking for granted that the actual thing that we sampled at the DW is always going to mean 0% deviation. So this thing here is okay. DW is this here, WT1. We sample some, well, let's say WT0. We sample this distribution to get a single value. Okay. Then we sample it again at T1. and we get another value. We take the difference between them, and that's how much it's fluctuated over that time interval T1 minus T0.
But it's the capital.
It'll change every single time step because it's a sampling process. Every single time we go from T1 to T0, then T2 to T1, then T3 to T2.
Is that you?
What it says, specifically, what does it say? What it says is that I have, let's say my deterministic part is just linear. Okay, so this is the integral of f of t dt. Nice linear integral. Okay, then what we've got is between t0 and t1, we've got w of t0, w of t1 minus w of t0. This term here comes from, let's say we'll call it this, WT1. Then we sample it again, we get another one. This is WT0. And then we take the difference between them. Okay? And then we do it every single time. Okay? And so what it tells us is that as T1 and T0 get closer and closer together, of course, this gets tighter and tighter and tighter, but proportionately it remains the same relative to the constant part, right? So that's the thing. So notice that T1 and T0 play really central roles in both dt and d. Okay. So if your noise is really strong, then taking the limit doesn't change it. Yeah. Okay. So this is what it looks like. So this equation is actually not so easy to do. Because the object sigma dw sigma wt1 minus wt0 does some awkward things in its limit. Okay, it's not in some certain technical senses, it's not terribly easy to do. What is interesting though, and what I do want to emphasize, is that what actually happens in practice is if we continue to zoom in on any stochastic process, on any process dw, what's happening is we're going from wt1 minus wt0, where T1 and T0 are getting closer and closer and closer together. What's actually happening is that in the stochastic process, we're actually getting closer and closer and closer in on that stochastic process, but it's still stochastic all the way down. It never stops being stochastic. Okay? That's really important to sort of grasp. The underlying mathematics tells us, this isn't necessarily true in practice, mathematics tells us that we have an arbitrarily deep stochastic process, and we can never get away from it no matter how closely we look at the data. Okay, that's what dw literally means. In practice, it's just as an approximation in the same way dt is an approximation. We can never get infinitely small time intervals in order to do calculus. In the same way, we never get infinitely small stochastic processes, but it's the way in which we do the mathematics. Okay. Because it's turtles all the way down. So this was first, I think, from Bertrand Russell when he was talking about a public lecture on astronomy. So he describes how the Earth orbits around the sun Now, the sun, in turn, orbits around the center of a vast collection of stars called a galaxy. At the end of the lecture, a little old lady at the back of the room got up and said, "What you've told us is rubbish. The world is really a flat plate supported on the back of a giant tortoise." And so Bertrand Russell says, at a superior smile, reply, "What is the tortoise standing on?" "You're very clever, young man, very clever," said the old lady, "but it's turtles all the way down." So we literally do have turtles all the way down in terms of the way in which stochastic processes work. It is stochastic all the way down. But we might have some nice linear approximation to some broad change in the system that we're looking at. Okay. So even though at some infinitely close time frame, these are really close, infinitely close to one another, they do cluster around a deterministic part of the system. Okay. Okay. On your computers in front of you, can you just quickly do a search to see if you can find if Mathematica has been installed on the desktops? It should have been. Anyone found it? No? It is installed. Excellent. Okay. So if you're working from your own laptop, hopefully you've got Mathematica installed already, or you can grab it from the terminals that you're working on. I want us to start thinking about how we might actually put this into a bit of code. Okay. So I want to talk about, first of all, one of the simplest possible processes that has some stochastic aspect to it. Okay. And so that process is called Brownian motion. Okay. And what's Brownian motion? It is that pollen suspended in a fluid that we had before that was just being bounced around. That was Brownian motion. Okay. It's named after a physicist, named after a physicist by Einstein. I think Brown might have been around in the late 19th century. And he, I think, was the first one that thought about these stochastic processes. And then Einstein came along and formalized it and gave it all the structure that was needed technically. And then Einstein named it after Brown and calling it Brownian motion. Now, we have a rate of change equation, dxt equals sigma dw. Before we move to, so this is the stochastic term here. But before we worry about that, what would this look like if it were a different system where it was deterministic? Dxt equals, let's say, x squared dt. Okay. If this is the system that we were interested in, the way in which we would have come by this system would have been something that looked like dx dt by dt equals x squared. Okay. And then we can translate that to this equation here, dx dt equals x squared dt. Okay. And of course, that just means that the thing that we're interested in, the incremental changes in the thing we're looking in, is described as some function multiplied by some small interval of time. And if we then wanted to solve that, the way we would actually do it is we would integrate dx dt equals integral x squared dt. Okay, so that's going to be 1/3 x cubed equals xt. That's all we do. This is bog standard high school calculus, nothing terribly interesting in it. That's what all of that is. Okay. However, we could, if we wanted to, then write x squared dt plus sigma dw. And now we've got our traditional deterministic part plus some noisy part. Okay. So if you recall earlier in the lecture, I promised you that I'd show you how to break up the equations we're going to be interested in terms of traditional physical continuous time series and some stochastic part. And so what we now do is our stochastic processes are linear combinations of a deterministic and a stochastic part, which is identical to the thinking that sat behind what Newton was doing when he broke up his equations into an infinite number of a linear combination of elements. But now I've got a linear, just a two-piece linear combination. Okay. But that isn't what we have. In fact, we've got a much simpler version of it than this. In fact, what we've got is just d of xt equals sigma dw. All that says is that our x is a function of some random variable. Okay. Now, if we were to now say I want to integrate this, I could say dxt, exactly how I did it before, equals some integral sigma dw, exactly what I did before, but now instead of integrating the deterministic part, I'm just integrating the fluctuating part. Okay. Now, how do we think about integrating this? What does this actually look like? Well, what we had was this thing here, right? That we are continuously sampling. So at time 0, we get that point. At time 1, we get that point. At time 2, we get that point. At time 3, we get that point. At time 4, we get that point. Okay. Now imagine if I integrated this for an infinite amount of time. So I've infinitely sampled this normal distribution, and I've integrated all of them, summed up all of those values. What's it going to look like? It's literally going to be some Gaussian function, right? Literally, it's going to be, if we integrate all of the elements of the Gaussian over an infinite number of samples of that, and we sum them all together, it's going to look like the integral over our Gaussian. Or rather, it's going to look like our Gaussian. Okay. What does that mean in practice? It means that we started here at t0, and let's say, actually, let's say we are here, and this is x of t, and this is t0, and this is t infinity. What we're going to end up with is something which is just a sample, a continuous time sample of our Gaussian process. Okay. So that's all that's happening there. It's a continuous time sample of that. Right? Now, if I then said, how do I plot an infinite time series? I would find that's got a mean of that value. It's got a variance of that value. You see what I'm doing there? This fluctuating infinite number of times, and I want to measure what all of this is telling me. It's telling me that I'll get some values out here. Some will actually be a little bit higher, but most of them are going to be around this midpoint. Okay. And I could then take a histogram and then normalize that histogram, and it would look like a Gaussian. Does that make sense? Not sure everyone's convinced. Anyone got any questions about that?
Is it the original distribution?
It is, yeah.
So then wouldn't the maximum number be whatever?
The maximum number is going to be the mean. Oh, sorry, the center point is going to be the mean of the whole process.
Well, when you're integrating over each individual. What you're doing is you are sampling a continuous variable, right? And then the way in which you actually do it approximately is you bin them, right? So what you end up with if you did this approximately is you would put a sample bin in there, right? And this would now be some finite discrete. I mean, in this, right?
In this one here?
Is that graph of the noise? Is that your integration?
That's the integration there.
Oh, okay.
Yeah. This thing here is actually this bit here. This change of x and t is this thing here. Okay, so this is my x. And in fact, what we're looking at is variations around x. Okay. That makes sense to everyone? In fact, dxt. This is my actual change in time. Okay. This is the change. My actual path is going to look different from that. Okay. The actual path x of t is going to look like this. It's going to be much smoother. Okay. This is just my change. Okay. But my path is also a random process as well.
I thought it was Gaussian.
Random means Gaussian in this sense.
Oh.
Okay. Random and Gaussian. For the purposes of this discussion, everything I say is random is also Gaussian. So Gaussian is a random distribution, right? Oh, so sorry. No, just one second. Just can I just get the clarify? What's the? Yeah. It is. The changes are sampled from the normal distribution. So these are the changes. These are the DXTs. They're all sampled from this normal distribution. And then if I integrate all of those, what I actually get is this noisy path. Does that make sense? Sorry, I didn't mean to. Sorry, what was your question? Oh, you got it. Yep. Excellent. So typically, our change in X has to have a mean of 0 because our changes are being sampled from around this distribution. But when we integrate it, what we're actually doing is we're adding all of those fluctuations up. Okay, so we happen to get two fluctuations which go up at the same time, then we actually
get relatively far away from the mean. And it's quite easy to get 2, 3, 4, 5, 6, 7, 8 movements up in a row. But that would just look like up, 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 above zero, up, above zero. Okay, because this would just be the change relative to the mean of zero. And there's actually integration of that. Does that make sense? Okay. So, in Mathematica, this is how we would actually write it. So let's just go through the notation. So P is just some variable that we're going to declare. Now, the most important aspects of this equation are that this is the differential of our variable of interest. So this is our, up the top there, d of xt is this thing here, okay? And we're going to make it equal to d of w, okay? And here, what I've said is that dw implicitly has got a variance at the front here of 1. This is our variable of interest. So these two things here, d of xt and xt have to be the same. And then x is the things changing over time, starting from some value x0 over some time. And our w is going to be a Wiener process, mean zero, variance sigma. Okay, so in Mathematical, we can do it one of two ways. We can either make this sigma here a 1 and then put a sigma term there, or we can leave that as 1 and have a sigma term here. But they're both identical to each other in terms of the result we get. Okay. So this says that an incremental change in x is exclusively driven by an incremental change in the stochastic process. X is our dependent variable of interest, which is dependent on time. So we're going to have x, which goes from x0. T we haven't declared yet, we'll do that in a second. In fact, T is our dependent variable, our independent variable. And so what this does is it makes P, it's not a set of data points yet. Okay. Here it just says that P is this function. Okay, and there's not enough detail in this function to actually be able to calculate P, because we still need to know what sigma is, and we still need to know what x0 is. X0 is our starting point, sigma is our variance. So in order to turn it into a plot, a solution of our plot, this line plot will take whatever random function generates. So random function takes this stochastic process and assigns P, assigns / assigns the missing variables x0 to 0 and sigma to 0.1. And it goes from 0 to 1 in time steps of 0.001. That's our h, our time incremental time step, and it's going to generate 500 of those puppies. Okay. So what this code does is it generates 500 versions of this process. Okay. Why do we want 500 versions? Why is that interesting to us? Exactly. What we want to be able to see is we want to see loads and loads of these time series to see if we can see some pattern in the stochastic variation. One thing that we are often fooled by is if we just have one time series, we may think that some of the funky things that we see in that single time series might actually be interesting when they are nothing more than just a random variation that we would see in general. Okay. This baseline, directed thin line opacity thing, this is just a style for the plot. Okay. What we can also do is that we can just put in our function, our Ito process function, this is our stochastic process. We can enter it exactly the way we did it up the top in the first example. But in fact, now what we can do is we can calculate the mean of P of t and the standard deviation of P of t and the variance of P of t. Okay. And Mathematica will actually allow you, if it can find it, to give you the actual equations of these. Not just the numerical value, which you can solve by putting in the numbers that you want, but it will give you the complete equation if it knows the solution. So it will derive complete equation structures for you just by asking for the mean, standard deviation, and the variance, if it knows how to calculate those. Okay, and for these sorts of processes, it does. So if you want an exercise for working on at home, the first thing that you should do is, first of all, implement these two, make sure the code is correct, and it gives you the correct outcomes. And then second of all, start playing with these equations. D of xt equals dwt. Play with that. What happens when you set that to 1, put the sigma here, and then start by adding in a deterministic term. Let's say just a constant term. So it's then, what would it look like if it was some constant c dt plus dwt? Yeah. Then do the same thing down here and see what happens when you calculate the mean, standard deviation, and variance if you've got a slightly more complicated structure to this equation here. Now, in Mathematica, what you'll find is that Mathematica has a really extensive help files. Okay, so here, if you just type in normal distribution in the search bar, it will find all sorts of information on how to use normal distribution. Okay. Now, I have a notoriously bad memory, right? And so I continuously forget exactly how to use the particular processes or the particular functions in Mathematica. So it's got some really cool ways of helping you out. If you just take your cursor and you just run it over the thing you want to know about, it gives you a chevron, down arrow, which gives you a quick reference guide for how to use that function. Or if you hit information, it'll take you to the page which fully describes the function. And at the very bottom, it'll give you possible issues, properties and relations, applications, all sorts of information. Okay. I can't begin to describe just how good its help pages are. Okay. It's not an easy language to learn. The developers know that, and they put a lot of effort into the help pages. So I strongly, yep. Let me see if I can. Okay, so I do not know how. Let me see. Let me see. So under text styling, it gives you all the ways in which you can write particular text styles. Okay. So then if you hit escape, you get 3 vertical dots, and then DD, escape again. That gives you the derivative symbol. Okay. So a lot of the symbols, so for example, pi is escape, pi, escape, and that gives you the letter pi. Okay. So escape is it's a modifier for any system defined value. Okay, so for example, any system defined character. So what's another good example? Lambda, for example, is escape, lambda, escape, and we get the mathematical, we get the Greek letter, get the Greek letter lambda. Okay, so that's where that's coming from. There's also escape, DD, escape gets you the differential little d, which you then multiply by t or WT. Okay. But of course, like every coder, I'm lazy as can be, so I copy a lot of my scripts. Okay, and it makes your life a lot easier. So a lot of my stuff is copied from and then modified from the help files. Sometimes quite extensively, sometimes not. It just depends on how useful the original problem was. But what we've got here, so this mathematical notebook is already up on the course web page for week 1. And so what we've got here in the output is 500 examples of the stochastic process of a simple diffusion over time. Okay. If all we wanted to do was measure the actual change, which is dWt, what dWt is the change between one time step and the next of one of these time series. Okay. The integral is this whole path that we're looking at here. Okay. And then then we can make this a little bit more funky. So again, this is just another Ito process. And again, it's just the dxdt equals dwt. So nothing's changed there. The starting point now is 3, and the standard deviation, or sorry, the variance is 0.1. But what I can do now is I can calculate the mean directly, but I can also calculate the variance directly by substituting in a starting point and sigma value. And what it tells me is that 0.01 t is our variance. Okay. Now we should know that, because we know that for a Gaussian process, the variance is a function of time. So it's the square root of the function of time. Okay. And because our variance is 0.1, then we know that's probably going to be 0.01 t when we integrate it. Okay. And then we can put some boundaries around it. So what I've done here is I've plotted some boundaries on it, right? So I've taken the mean of f and the variance of f. So this is the mean of f, and this is the variance of f.
so mean of PT, and simplify the variance of PT for X starting at 3 and sigma being 0.1 for both the mean and the variance, of course. And now what I can plot is the mean minus 2 times the root of the variance and the mean plus 2 times the root of the variance. And what that tells me is plus or minus 2 standard deviations. Okay. Do you follow that? And so what's going on there is that now we can see in this curve how our standard deviation, 2 standard deviations, are changing plus or minus the mean. And we would expect to see almost all of the paths to be within 2 standard deviations of the mean. Okay, not all of them, because it's only 2 standard deviations, but a lot of them. And I can now continue to do some further sort of analysis on what's going on to take, what we can do is we can take slices of our data in order to see what's going on. And I mentioned before that what Mathematical will do is if we don't provide it with sufficient information to work out the numerical value of the mean, the standard deviation, and variance, it will provide it to us in a symbolic form. Okay, what does that mean? It means that the standard deviation, because here it doesn't have enough information, it actually gives us the standard deviation in terms of time. Okay, and the standard deviation is actually now a function of time, it's the square root of time. And we can see how that's the case because we pop up here, this curve here, this orange and then this blue curve, we see that they look like square root functions. Okay, and they look like square root functions because the variance, or sorry, here the standard deviation is increasing as the square root of time. Okay. And so if you wanted to look up the standard deviation, you would find that as your samples increase, it's actually as a diffusion process. So if you looked up Brownian motion as a diffusion process, you'd see that its standard deviation will be a function of time. As time goes on, process gets broader and broader and broader. Okay, so standard deviation gets larger and larger over time. The next one, this is what I was suggesting before, or at least this is the deterministic version of it. So now we can just look at really simple differential equations. So here we're going to use dsolve, which is differential solutions. So we can find out what they look like. So dsolve puts an equation, some U2, a variation which is changing over time, there's some x min and x max, and it will solve the equation. Okay. And so here is our rate of change, x prime of t. So prime in Mathematica tells us that that's our rate of change. Now, rate of change here is a constant value mu. It's going to start from some x0 equals a, and x is our dependent variable and t is our independent variable. Okay. And then we're going to evaluate it with 3 different values. One with a goes with a equals 0 and a mean of 0.5, one with an a of 1 and a mean of 0.2, and a of a value of -3 and a mean of 2. And I'm going to integrate that from t from 0 to 2. Okay, and what it tells us here is that first of all, when it solves that equation, so desolve, when that solves, this is the output. It says that x is a function of t, a plus t mu. Okay, and it's linear, a plus t mu. So it's linear in t with a constant a and a gradient of mu, because we started with a rate of change whose value is mu. So any integral of a constant is going to be a linear equation. And so now we've got is 3 equations with different starting points, different x zeros. So if we look at our start point, that's these a's here. We have a starting point of 0, 1, and -3. So 1, 0, -3. And each one has a different gradient. And the gradients are related to the mu terms. So that's simply how we integrate really simple equations. But now we can have an Ito process, which we can play around with a bit. I said earlier on that usually we would just let our Wiener process just be with a variance of 1 and a mean value of 0. But in fact, we can allow it to have a mean, which is 0.5, as I've got here, and a variance of 0.1. So what do you think having a Wiener process with a shifted mean value is going to do to our stochastic process? Any ideas? Exactly. And that's what we observe. So note that this is actually just what looks initially like a standard Brownian process. But because our Wiener process has a non-zero mean, it's going to drift. And we can tell whether by inspection which of these is the mean, which one is the standard deviation. Because we go from 0 to 1, and we have what looks like a rise of about 0.5 on average. It's certainly not 0.1. And that tells us that this must be our drift. Okay, and this must be our variance. Even if we didn't know exactly what the Wiener process actually is, and there's the mean and the variance. Okay. Now we can do something which is slightly more complicated. And we can ask for the probability distribution function of an Ito process. Okay. What's the probability distribution function? Well, what I want you to imagine is that if we take this stochastic process up here, this Ito process here, and we drew a line through it, let's say 0.4, we can imagine if we had an infinite number of paths going through 0.4, what we'd end up with is the distribution of points that go through 0.4. And we could ask, well, in general, what does that distribution look like for any value of t? Well, the PDF is just that. The PDF is the evolution of that distribution over time. So we took a time slice at 0.4, and we substituted t equals 0.4 into this equation here. We would find that we get a numerical value which would tell us what the distribution should look like at that point. Okay, it'll still depend on X because it's a stochastic value. X is our vertical axis here. Okay, so it's a distribution over X, and this tells us what that distribution looks like. Does that make sense? Okay. And this is the more conventional way of writing our Wiener process. So now our Wiener process here on the right-hand side doesn't have any values, which means it's going to default to 0 and 1. And over here, we have 0.5 and 0.1. And so statistically, the plot that we get here is going to be identical statistically to this one here with a Wiener process of 0.5 and 0.1. Okay. So those two should be statistically identical. Okay. Anyone got any questions about that?
What is the ETO process?
The ETO process, what it's actually doing is it's storing the mathematical functions, the computational functions that it needs in order to generate the volatile path, and then it doesn't compute it yet. It only computes it once you run a random function over the top of it. Okay, random function actually generates, what random function is doing is actually sampling this. And then by implication, it actually integrates it. Because what it does, so P equals some random function, and it's got a whole bunch of parameters in there, right, that haven't been declared yet. So what the way that I'm declaring it in here, it says I'm not going to give it values until I actually need to give it values. So if you look at what's up on the screen at the moment, what's actually happening is I'm only giving it values like x0 when I need to evaluate the function. So it remains an implicit function, or rather undeclared function, until I need it. Only once I run random function does P get the values that it actually needs in order to be computed. And then what is it actually doing? It starts out by starting at x0. Starts out at x0, and then it computes first of all the gradient, which is so first of all it computes the 0.5 part, and then it computes this bit here. And so then that's going to come from some Gaussian distribution, and so it'll sample that, and so that's the actual point that it goes to. Okay, and now that's its new point. And so now it goes the deterministic bit, and then it finds an extra bit, which is actually the point that it goes to. Okay. Okay, now this workbook actually has a ton of stuff in it. In particular, if you look at what we see down here, we can do all sorts of interesting things in the limits of these processes, if the limits exist. They don't always exist. What it tells us is that what our functions look like if our time goes very, very large. Do we get stable? Do we get predictable solutions that we can play around with? I also put in a whole bunch of stochastic processes. I suggest at the very least you start playing around with those. Okay. What I really want to emphasize, probably more than anything else, is that every week I'm going to give you these notebooks. So there's going to be zero mystery in terms of what you need to code in order to be able to solve any problem or run any simulation that you need to run for this course. There's zero mystery. But you do need to know how to actually run the code, right? Like you'll need to know if you want to change something, what are you going to need to change is going to be important. Okay. And then if you run into trouble, how do you test your code in a sensible way? So you do need to know the basics of Mathematica in order to get this right. But the problem with Mathematica is that if you've just got a blank notebook, it's often difficult to get off the ground. Okay, it's often get the first bit of code right that does the thing that you want it to do. Okay, that bit's usually the hard bit. The easy bit is taking existing code and messing around with that until it works to do the thing that you want it to do. That bit's quite a lot easier. So I'm giving you that first bit so that you don't need to worry too much about writing from blank code. Now, are you about to leave?
Yeah.
Ah, crap. Okay. No, it's fine. Just check out the first assignment notes on online. That's all.
Oh, yeah, I already.
Oh, okay, great. Okay. So now, last for the session, assignment 1, article review. Okay, I said early on tonight that what you need to do, or sorry, you don't need to do this, but it might help to do this, to think about what you'd like to do for your nonlinear final report. Okay. I would recommend that you have a look at the what's necessary, what you have to do for your final report, just by skipping forward in the lecture material, or rather actually going to the assignments page and just looking at what's on the assignments page and reading that first, and then think about what you might want to do for your final assignment. In particular, if you've got something in nonlinear dynamics that you're kind of interested in, is it climate change? Is it disease propagation? Is it financial markets? Think about what you actually want to do, and then see if there's something in the list that's provided for the articles. See if there's anything in those articles which is close to what you want to do. Okay. You don't have to do it that way. It just might make things easier further down the track. So the first assessment, article review. Think carefully about the article you are reviewing. Okay, so first of all, how technical is it? There's a Goldilocks principle here. You don't want it to be too hard, and you don't want it to be too easy. Okay, if it's too hard, if you read it and it's completely makes zero sense to you, it's full of mathematics and it's completely beyond you, don't worry about it. Just don't do that one. Okay, so if you read it and it seems kind of trivial or uninteresting to you, don't do that one. Okay, find the one that sort of matches where you're at, that you will benefit, that you believe you will benefit most from by looking at. Okay, that's the bit that I want you to take away from that. Make sure it's relevant to the course. If in doubt, ask me, email me. Does it interest you? This will help you engage while reading it, and this might lead to further work you do in this course. Skim the article first. Ask yourself a few key questions. Does the conclusion surprise you or draw you in? If it does, good. How easy is the summary, the abstract, to comprehend? What sort of article is it? A review, technical result, theoretical, applied? So keep in mind what you're actually reading. Is it real or artificial data? Which do you want to work with, use and you potentially use in your later project? And do they describe how to get the data? And perhaps more importantly, do they describe how to use algorithms? Okay, papers with code rock. Okay, they make your life a lot easier to understand how to do things. And how well written is it? Check the section headings, plots, etc. Does it all look well structured? So when you look at it, do the writers make it easy to comprehend what's going on at a first skim? If it turns out that it's really hard to understand what they're driving at from a first skim, and perhaps even a slightly deeper second glance, they may not be great communicators. Just because it's been published doesn't mean that one, it's necessarily right, it might still be wrong. And two, just because it's published doesn't mean that they wrote very well. Do you think the article is believable? This is the final point. If you don't believe it, I might not believe it too. Okay, so you could attack the paper, which is a totally legitimate thing to do. And that actually might be a very useful way to start thinking about your own writing. But bear in mind that if you're wrong, that might suck. Okay. Okay, so first of all, refinement. initial review, and then selection. Okay. And that, in fact, is all I've got for tonight. Anyone got any questions about tonight? Any big burning questions you might have?
So the final or and review, it's okay if they compensate in different topics.
Yep, no problems at all. Absolutely no problems at all. Yep. I'm not sure if I say it in the assessment. So all of the articles that are available, all of the articles that are listed in the assessment are ones that you can use. I've listed those because what often happens is if you're confronted with Google Scholar, which is usually what we use to search for articles, right? Confronted with Google Scholar and you've got a topic you want to do. So you put in some keywords and you end up with 10,000 papers, right? And you have no idea which is a good one, what might actually help you do anything. So the ones that I've got there are ones that I've handpicked as to be good enough for this project, okay, for the first task. So if you just do one of the ones out of that list, at least the article is good enough, okay? You're not going to be working on some weird, horrible topic which is unrelated, won't get you very far, and won't give you any comprehending ideas about the course, okay? So they are good articles. But if you happen to find an article in a topic that you're interested in, but you're still not certain if it's good or not, you can certainly use it, but I'd highly recommend that you email me with your alternative suggestion, just so at least I can have a look at it and just see if it's actually an okay article, okay? Just in case, for whatever reason, there are plenty of people who've written wrong things that have been published, okay? And I'd hate you to go astray, okay? But I also want to make it a little bit easier than having no leads whatsoever. So that's what those articles are that are there. They are leads. Okay. Any other questions? Good question. Good question. For the final report, this is obviously an empirical unit, which means that data is important. Okay. But you can simulate data. Okay. So one way in which we test a lot of our theories is we have a real world set of data, and then we have some simulated data. Okay, and we run a comparison between the real world data and simulated data. And we then try and make them sort of compare to each other and see whether our simulated data matches up with our expectations for real data and vice versa. Okay. So if you just wanted to, if you couldn't find real data, but you wanted to run some simulations and then test whether your methods work on your simulated data, that's a perfectly legitimate thing to do. That's perfectly fine. Okay. But it's easy to test simulated data. It's much harder to test real world data. Okay. So there are very simple things you can do with simulated data that will, and we'll do those simulations during this course, that will illustrate the points that we're talking about this semester. Okay? Very simple to do that. So that's probably not going to get you very many marks in terms of originality. Okay. So if you're going to use simulated data, the analysis will need to be deeper. Okay, that's the only thing I'll say. Okay. Other questions? All right, rock and roll, guys. Thank you so much. Enjoy, and I will catch you all in a week's time.